So here you are, lying in bed or sitting on your couch, scrolling through your phone. The screen glows, the apps load, the messages send. Everything works perfectly, seamlessly. You don't think about how any of it works. You don't think about the millions of lines of code running behind that little screen. You don't think about the satellites orbiting above you, the fiber optic cables beneath the ocean floor, or the power plants generating the electricity that keeps your world running. But here's something that might surprise you. On November 8, 2023, 10 million Australians woke up to a world where none of that worked. No internet, no mobile service, no way to call emergency services, hospitals couldn't admit patients, banks couldn't process transactions. The entire country's transportation network ground to a halt. 9 million people, a third of the population, were suddenly disconnected from the modern world. The cause? A software update. One routine, supposedly minor update to a routing system that was supposed to improve network performance. Instead, it brought an entire nation to its knees. Then, on July 18, 2024, it happened again. But this time it wasn't one country, it was the entire planet. 8.5 million computers suddenly displayed the infamous blue screen of death. Hospitals cancelled surgeries, airlines grounded flights, emergency call systems went dark, and the culprit was the same: a software update. An update to a security system. A system designed to protect computers from threats became the threat itself. And then, on April 28, 2025, the entire Iberian Peninsula went dark in 90 seconds. 45 million people across Spain and Portugal lost power. No lights, no phones, no refrigeration. Hospitals running on emergency generators, subways stranded between stations. All because of a single point of failure in the power grid. One malfunction, one moment of chaos, and the lights went out across 2 countries. What connects these stories? They reveal a terrifying truth about the world we've built. We've constructed systems of incredible complexity to make our lives safer and more convenient. Airplanes that fly themselves, power grids that span continents, financial networks that transfer billions in milliseconds. But that very connectedness, that incredible interdependence, has created a new kind of vulnerability. A single mistake in one place can ripple outward and bring everything crashing down. A single point of failure, a single wrong assumption, a single overlooked detail can trigger a cascade that destroys the entire structure. Think about that for a second. Every building you enter, every bridge you cross, every plane you board, every app you open is an assumption, an educated guess, a bet that engineers have made about how the world works.
And sometimes, rarely, but catastrophically, that bet is wrong. Now let me ask you something. Have you ever felt that moment of inexplicable dread when you realize your entire life depends on systems you don't understand? When your power goes out, or your internet dies, or your brakes fail, and you suddenly understand how fragile your world really is. That moment when you realize that a civilization's worth of engineering is only as strong as its weakest link. Have you ever wondered how the things we build can fail so spectacularly? And more importantly, why do we keep making the same mistakes? Because here's what I want to show you. The history of engineering is the history of learning through failure. Every collapse, every explosion, every crash has taught us something. The engineers who came before us made mistakes so that we don't have to. They crashed planes so we can fly safely. They built bridges that fell so we can build bridges that stand.
They made terrible, costly,
sometimes deadly errors, so we could learn what not to do. This is not a story of incompetence. This is a story of resilience. It's a story of how failure becomes the engine of progress. It's the story of how we keep trying, keep improving, keep building, despite everything that can go wrong. Henry Petrosky, the engineer and historian, wrote in his book, To Engineer is Human, that engineering is fundamentally about anticipating failure. Every design is a hypothesis. You build something and you watch it, waiting to see if it will stand. And when it falls, when it collapses, you have learned something you could never have learned any other way. You have discovered the limits of your knowledge. You have found the place where your assumptions failed, and you will never make that mistake again. Imagine you are standing on a hilltop, and below you is a city you've built yourself. Every building, every road, every bridge, every power line, every pipe,
all of it is your design. Now imagine that you can watch this city for 100 years, 1,000 years, and see what fails first. See which building cracks, which bridge collapses, which pipe bursts. Would you be surprised? Or would you nod, take out your notebook, and fix it for the next generation? The answer is the latter. That's what engineers do. They build the city, and they watch it, and they learn. And every time something breaks, they understand something new about the world. They get another piece of the puzzle. So here we are. We've built our cities. We've erected our skyscrapers. We've dug our tunnels. We've launched our satellites. We've built the most complex systems in human history, and they work brilliantly most of the time. But when they fail, they don't fail small. They fail catastrophically. This is our story for tonight. We're going to take a deep, slow dive into engineering disasters, not to scare you, but to show you how the world really works. To show you that every failure is a lesson waiting to be learned. To show you how engineers think, how they anticipate failure, and how they use catastrophe to build a better world. We'll start with the basics. What is an engineering disaster? How do we define failure? What separates a simple mistake from a catastrophic event? And why does one small error sometimes cause a cascade of destruction that brings down entire systems? We'll explore the history of failure. We'll go back to the origins of engineering, to the early days when people built bridges and buildings and ships, and learned the hard way that their designs were flawed. We'll see how the great engineering disasters of the 19th and 20th centuries forced changes in building codes, safety standards, and engineering education. We'll look at catastrophic failures in all their forms. Structural collapses, like the Skyline Plaza apartments in Virginia, or the walkways at the Hyatt Regency in Kansas City.
Industrial disasters, like Bhopal, Deepwater Horizon, and Chernobyl. The failures of great machines, like the Ford Pinto, the Space Shuttle Challenger, and the Boeing 737 MAX. And the new kind of disaster, the one that emerged in the 21st century, the software failure, like CrowdStrike and Optus. And at the heart of it all, the one thing that ties all these disasters together, the cascade, the chain reaction, the moment when a series of small, seemingly insignificant failures link together and become inevitable. Because the vast majority of engineering disasters aren't caused by one big mistake. They're caused by dozens of small ones, each individually not catastrophic, but when combined, devastating. We'll explore the role of human error, the tendency of people in authority to ignore warnings, the pressure to complete projects on time and under budget, the psychological blind spots that lead bright, experienced engineers to make decisions that, in hindsight, seem obviously wrong. We'll see how engineers investigate disasters, how they become forensic detectives, analyzing twisted metal and shattered concrete, reading data logs and interviewing survivors, how they turn the wreckage into a lesson, how they use the disaster to make the world safer. And finally, we'll look to the future. We'll see how the lessons learned from past failures are being applied to the problems of tomorrow. From the International Thermonuclear Experimental Reactor, ITER, to self-driving cars, to quantum computing, the same principles apply. We can't afford to get it wrong, but we will, and we'll learn, and we'll get better. So settle in, take a breath, let yourself be curious. I'm going to walk you through the most fascinating, disturbing, and hopeful stories about engineering failures you've ever heard. No technical jargon, no dry academic tone, just a good, slow, honest conversation about the things we build and the ways they break. You're about to see the world differently. You'll walk into a building and see the assumptions behind the walls. You'll get into an elevator and think about the cables that could fail, but also about the safety systems that were designed precisely for that scenario. You'll open an app and realize that someone, somewhere, tried to anticipate every possible way it could fail. And when it does fail, someone will be watching. Someone will be documenting, analyzing, and learning, and they'll make it better. Because that's what we do. We build, we fail, and we learn. And each time we fail, we get a little closer to getting it right. Now, before we go any further, I should warn you. This is a story that builds slowly. We're going to take our time. We're going to be thorough. We're going to follow the chain of events from the first mistake to the final catastrophe. We're going to look at the details, the human decisions, the engineering compromises, the blind spots. And we're going to understand, really understand, why things go wrong. Because only then can we appreciate how right things usually go. Imagine you're standing on a hill overlooking a river. It's a grey November morning in 1940, and below you, a bridge is dancing. Not the kind of dancing you'd see at a ballroom, but the slow, rhythmic, terrifying sway of steel and concrete being tortured by the wind. The Tacoma Narrows Bridge, known locally as Galloping Gertie, is famous for exactly this. It sways, it twists, it undulates like a snake, and the men who built it watch from the shore in horror, knowing that their beautiful, elegant bridge is about to die. 2 hours later, it does. The bridge collapses into the waters of Puget Sound. No one dies, thank goodness. But the footage of that bridge twisting itself to pieces becomes one of the most famous engineering videos in history. It was the day engineers learned a lesson they'd never forget. Sometimes, the most beautiful design is the most dangerous. The Tacoma Narrows Bridge was built to be a marvel. It was a suspension bridge, a type of structure that was becoming increasingly popular in America. The Golden Gate Bridge had opened just 3 years earlier, and it was a triumph. The Tacoma Narrows Bridge was supposed to be its smaller, more elegant cousin. The designers wanted it to be light. They wanted it to be graceful. They wanted it to be cheap. And they got what they wanted. The bridge was so light that it swayed in a moderate breeze. It was so graceful that it looked like it was made of paper. And it was cheap, which meant that the engineers had to sacrifice something. What they sacrificed was safety. You see, suspension bridges rely on a simple principle. You hang the road deck from cables which are strung between towers. The weight of the deck pulls down on the cables, which pulls down on the towers, which transfers the load to the foundations.
It's an elegant system, but it has a weakness. The deck must be stiff enough to resist wind. If it's too flexible, the wind can make it bounce. And if it bounces at just the right frequency, it will enter a feedback loop of destruction. The engineers who designed Galloping Gertie didn't think about that. They thought about cost. They thought about aesthetics. They thought about making the bridge light and graceful. They didn't think about the wind. And on that November morning, the wind did what wind does. It started at a modest 15 miles per hour. The bridge began to sway. The swaying changed the shape of the bridge, which changed the way the wind hit it, which made it sway more.
Soon, the bridge was twisting back and forth by 20 feet. The concrete deck began to shatter. The cables snapped, and the entire structure plunged into the water. Now, let's pause for a moment. What did the engineers learn from this disaster? They learned that you can't ignore aerodynamics. They learned that a bridge is not just a static structure. It interacts with the environment. It has to be designed to handle the forces of nature. And they learned that cost-cutting can be deadly. But the most important lesson was this: a successful structure is not just one that stays up. It's one that anticipates how it might fall. It's one that builds in safety margins. It's one that has redundancy, multiple paths for failure, so that a single weak point doesn't bring the whole thing down. This is the first principle of engineering thought: to anticipate failure, to know where the weak points are, to build a structure that can withstand not just the expected loads, but the unexpected ones, the ones you can't predict. Now let's jump forward 41 years to Kansas City, Missouri. It's July 17th, 1981. The Hyatt Regency Hotel is hosting a tea dance. It's a summer evening, and 1,600 people are packed into the lobby. Above them, suspended from the ceiling, are 3 skywalks made of glass and steel. They're beautiful, they're modern, they're the signature feature of the hotel, and they're about to kill 114 people. The skywalks were designed to be suspended from the ceiling by a series of steel rods. The rods would pass through the second-level walkway and connect to the fourth-level walkway. It was a clever design that allowed both walkways to hang from the same set of supports. But there was a problem. The design required a single long rod that would pass through the second-level walkway without bearing any weight. The second-level walkway would be supported by nuts, threaded onto the rod above and below its floor. When the engineers looked at the plans, they realized that they couldn't thread the nuts onto the rod above the second-level walkway. It was too difficult to access, so they made a change. Instead of one long rod, they would use 2 shorter rods. One rod would connect the ceiling to the second-level walkway. Another would connect the second-level walkway to the fourth-level walkway. It was a small change, a simple change. It saved a few hours of labor, but it changed the load path completely. In the original design, the fourth-level walkway was supported by the same set of rods as the second-level walkway. The load of the fourth-level walkway was transferred directly to the ceiling through a single rod. The second-level walkway was just along for the ride. But in the revised design, the fourth-level walkway was supported by rods that were attached to the second-level walkway. The second-level walkway now had to support not just its own weight, but the weight of the fourth-level walkway. The engineers never recalculated the load. They never tested the connection. They assumed that the change was harmless. They were wrong. When the skywalks collapsed, they came down like a house of cards. The fourth-level walkway fell onto the second-level walkway. The second-level walkway fell onto the crowd below. 114 people died, many of them crushed instantly. It was the deadliest structural collapse in American history at the time. It still is one of the worst. Now, what did we learn from this disaster? We learned that assumptions can kill you. We learned that even a small change to a design must be thoroughly analyzed. We learned that the failure of a single connection can cascade through an entire system. And we learned that the people who build things must be held accountable. But there was another lesson, a deeper one. The failure wasn't just an engineering failure. It was a management failure. It was a communication failure. It was a failure of the whole system of checking and verifying and reviewing. The engineers who made the change didn't tell the engineers who did the calculations. The people who approved the change didn't understand the implications. And the people who built the walkways didn't know what they were assembling. This is a pattern you're going to see again and again in this story. The breakdown of communication. The assumption that someone else is checking the details. The pressure to save money and time. And the failure to ask the simple question, what if this goes wrong? Henry Petrosky, in his book, To Engineer is Human, writes about this exact phenomenon. He argues that engineering is essentially a discipline of failure. Engineers learn not from their successes, but from their mistakes. Each failure teaches us something we never knew before. Each collapse reveals a weakness we hadn't considered. And this is the beautiful irony of engineering. The failures are the best teachers. The buildings that fall, the bridges that collapse, the systems that fail. They're not tragedies. They're lessons. They're the only way we learn the limits of our knowledge. Let's go back to the Tacoma Narrows Bridge for a moment. After the collapse, engineers realized that they had to understand wind better. They had to study how buildings and bridges interact with the air. They had to build wind tunnels and test models. They had to develop new mathematical models to predict the behavior of structures under wind loads. Today, every suspension bridge in the world is designed with these lessons in mind. Engineers test every design in wind tunnels. They build models and watch how they behave. They use computers to simulate thousands of scenarios. All because of one failure. All because a bridge twisted itself to pieces in 1940.
And the Hyatt Regency walkways, they led to a complete overhaul of building codes. New regulations were created for the inspection and approval of structural connections. New standards for the training of engineers. New requirements for independent review. All because 114 people died in a hotel lobby. All because of a misunderstanding about a steel rod. Here's the thing you need to understand. The engineering profession is not about getting it right. It's about getting it less wrong each time. It's about learning from the mistakes of the past and applying those lessons to the future. It's about constantly questioning assumptions, about building in safety margins, about creating systems that can handle the unexpected. And we've gotten much better at this. Our buildings are safer, our bridges are stronger, our systems are more reliable. But we still make mistakes. We still fail. Because we're human. Because we're limited. Because we can't predict everything. But here's the important part. When we do fail, we learn. We study the failure. We understand it. We apply the lesson. And we move forward. In the next chapter, we're going to see how this process works. We're going to look at the most complex systems ever built. The ones that protect us from our own worst impulses. And we're going to see how those systems can fail, often in the most surprising ways. There's a moment in every engineering disaster that haunts the people who study them. It's the moment when the systems designed to prevent failure become the cause of failure. When the safeguards, the backups, the redundancies, the very things meant to keep us safe, turn against us. It's the moment when protection becomes a trap. On March 28, 1979, at 3 in the morning, the control room of the 3 Mile Island nuclear power plant in Pennsylvania started screaming. Alarms were going off everywhere. Red lights were flashing.
Operators were running from panel to panel, trying to understand what was happening. What they didn't know was that they were already in the middle of a disaster. The reactor had just experienced a routine maintenance issue. A pump had stopped working, and the cooling system had automatically shut down to protect itself. That's what it was supposed to do. The backup cooling system kicked in, as it was designed to do. Everything seemed to be working. But the operators couldn't see what was really going on. Their instruments were telling them a story that wasn't true. You see, the reactor had a system called a pressurizer. It was a big tank of water and steam that helped control the pressure in the cooling system. The operators were trained to watch the water level in the pressurizer. If it was high, the reactor was running properly. If it was low, there was a problem. On that morning, the water level in the pressurizer was very high.
The operators thought this meant the reactor was full of water. They were wrong. The water level was high because steam had pushed the water up, creating a bubble of steam at the top of the pressurizer. The reactor was actually losing coolant. It was overheating, and the operators, trusting their instruments, were about to make a terrible mistake. They decided to turn off the backup cooling system. They thought it was flooding the reactor. They were trying to prevent damage. Instead, they caused it. The reactor continued to overheat. The fuel rods began to melt. Radioactive gases were released. It was the most serious nuclear accident in American history. Now, let's pause and think about this. The operators at 3 Mile Island were not incompetent. They were highly trained professionals. They had done everything right based on the information they had. But the information they had was wrong. Their instruments were designed to tell them what was happening in the reactor.
But they were designed before anyone had thought about what would happen if the reactor started losing water. The instruments were giving them data, but the data was being misinterpreted. This is what engineers call a latent failure. A problem that's built into the system from the beginning, waiting to be triggered by the right combination of events. It's not a failure of the equipment. It's a failure of design. A failure to anticipate all the ways things could go wrong. The investigation after 3 Mile Island revealed a shocking truth. The operators had been trained for years on simulators. They had practiced every possible scenario. But they had never practiced this one, because no one had ever imagined it. No one had thought about what would happen if the instruments started giving misleading readings. The lessons from 3 Mile Island changed everything. Every nuclear plant in the world was re-evaluated. New procedures were created for operators.
New instruments were installed. New training programs were developed. And the industry, which had been expanding rapidly, came to a grinding halt. It would take decades for nuclear power to recover. Now, let's jump forward 45 years to November 8th, 2023. A different kind of alarm is going off. In Australia, millions of phones are dead. No signal, no internet, no calls. The Optus network, one of the largest in the country, has simply vanished. What happened? It was a software update. The engineers at Optus had decided to upgrade the routing software on their network. They wanted to improve performance. They wanted to add new features. They wanted to modernize. But the update contained a flaw. When the update was applied, it caused a cascade of failures. Routers started rerouting traffic in ways they weren't supposed to. The network became unstable. And then it crashed. All of it, at once.
The engineers at Optus had designed their network with redundancy. They had backups. They had fail-safes. They had systems that were supposed to detect problems and shut them down before they got out of control. But the update had a bug that bypassed all of those systems. It was like a virus that the immune system couldn't see. 10 million people were left without service. Hospitals couldn't call ambulances. Banks couldn't process transactions. Train networks ground to a halt. It was chaos. And it was all because of an update that was supposed to improve things. Now, think about that for a moment. A system designed to be more reliable became less reliable because someone tried to improve it. This is the paradox of modern engineering. As we add more complexity, we add more potential points of failure. As we build more safeguards, we build more ways for things to go wrong. There's a concept in engineering called defense in depth.
It's the idea that you should have multiple layers of protection. Each layer should be independent of the others. So if one fails, the others still work. It's a sound principle, but it has a flaw. If the layers are designed by the same people, using the same assumptions, they can all fail in the same way. This is what happened at 3 Mile Island. The instruments were all designed based on the same assumptions. When those assumptions proved wrong, all the instruments were wrong at the same time. The operators had no way to know what was really happening. And it's what happened with Optus. The network was designed with redundancy, but the redundancy was all based on the same software architecture. When the architecture failed, the redundancy failed too. Everything went down together. Let's look at another example. July 18th, 2024. Millions of computers around the world suddenly displayed the blue screen of death. Airplanes couldn't take off. Hospitals had to turn patients away. Emergency services went dark. The cause was an update to a security system called CrowdStrike. CrowdStrike is a company that sells security software. Their product runs deep inside your computer, at the kernel level. It's designed to catch threats that other systems miss. It's powerful, it's effective, and it's very, very invasive. The update that caused the problem was supposed to be a routine change to the security configuration. It was a small file, only a few kilobytes in size. It was tested, or so the company thought. But the file contained an error. It told the kernel to read a piece of memory that didn't exist. The kernel crashed, the computer crashed, and the whole world crashed with it. What's fascinating about this disaster is how quickly it spread. The update was pushed out automatically to millions of computers around the world. Within minutes, it had disabled critical infrastructure on every continent. It didn't matter if you were in New York or London or Tokyo. If your computer was using CrowdStrike, your computer was dead. And here's the real kicker. The people who were affected were the ones who took security seriously. They had installed CrowdStrike specifically to protect themselves. They had done the right thing, and they were punished for it. Their security system had turned into a weapon of mass destruction. This is not a new phenomenon. In 1999, a similar thing happened at the National Security Agency. The agency banned employees from bringing in a popular toy called Furby. Why? Because the Furby could record what you said and play it back. The NSA was afraid it would be used to spy on them. The irony, of course, is that the agency exists specifically to spy on everyone else. They were afraid of a children's toy. The pattern is everywhere. We build systems to protect ourselves. Those systems become complex. The complexity creates vulnerabilities. Those vulnerabilities are exploited. And the systems that were supposed to protect us become our greatest weakness. This is why engineers talk about the cascade effect, when one failure leads to another, which leads to another, creating a chain reaction that brings the whole system down. It's like a line of dominoes. You knock one over and they all fall. At 3 Mile Island,
The cascade was slow. It happened over hours. The operators had time to think, but they didn't have the information they needed. They made decisions that seemed right, but were wrong. The cascade continued until the reactor was damaged beyond repair. At Optus, the cascade was faster. It happened in minutes. The network was saturated with traffic, and the routers couldn't keep up. They started dropping connections. Then they started rerouting traffic in loops. Then they crashed. The whole system died in a matter of minutes. At CrowdStrike, the cascade was almost instantaneous. The update was applied. The kernel crashed. The computer died. In seconds, millions of machines were dead. What connects these disasters is the assumption that the system will fail gracefully. That if something goes wrong, it will fail in a way that doesn't take everything else down. This is called graceful degradation. It's a key principle of engineering. A good system should degrade gracefully. It should fail slowly. It should give you time to respond. But the systems we're building today aren't degrading gracefully. They're failing catastrophically. One small error is bringing everything down at once, and we're not learning from our mistakes as quickly as we should. The reason is complexity. The systems we're building are so complex that we can't understand all the ways they might fail. We can't test all the scenarios. We can't foresee all the consequences. We're building systems that are smarter than we are, and they're starting to show it. This brings us to the most important question of our time. If we can't understand our own systems, how can we make them safe? There is no easy answer, but there is a path forward. And it starts with the humility to admit that we don't know everything. To build systems that can be understood. To create redundancies that are truly independent. To learn from failures, not just in our own systems, but in the systems of others. The investigation after 3 Mile Island took months, but the lessons from that disaster are still being learned. The investigation after Optus took weeks. The investigation after CrowdStrike is still ongoing. Each time we learn something new. Each time we understand a little better how these complex systems work. And maybe that's the most important lesson of all. Engineering is not about getting it right the first time. It's about getting it right eventually. It's about learning from failures and applying those lessons to the future. It's about constant improvement, constant vigilance, constant questioning. We'll never be perfect. We'll always make mistakes. But we can learn. And that's what makes us human. That's what makes engineering possible. Have you ever watched one of those crime shows where detectives walk through a crime scene, examining every detail, looking for clues? They study the blood spatter, they photograph the footprints, they interview witnesses, they piece together a timeline of exactly what happened. Then they use that timeline to figure out who did it and why. Engineering disasters are investigated the same way. Except instead of detectives, we have engineers. Instead of a crime scene, we have a disaster site. Instead of blood spatter, we have twisted metal. And instead of catching a criminal, we're trying to catch a mistake, a design flaw, a failure of the system. This is called forensic engineering, and it's one of the most fascinating and most important fields in all of engineering. It's the art of understanding how things break. It's the science of turning debris into knowledge. Let me tell you about a man named Anthony Sophronis. He was a senior engineer at ExxonMobil, one of the largest companies in the world. He spent his career investigating disasters, pumps that exploded, pipes that cracked, structures that collapsed. He'd go to the site, look at the wreckage, and figure out what went wrong. He wrote a book called Decoding Disasters, where he explains his methods. According to Sophronis, forensic engineering is a lot like doing a puzzle. You have a pile of pieces. You don't know what the picture is supposed to look like, but you have to put it together anyway. You start with the obvious pieces, the big ones, the ones that are easy to identify. Then you work your way to the smaller pieces, the ones that are harder to place. Eventually, if you're patient enough, the picture starts to emerge. But here's the challenge. The pieces are often damaged. They're burned, they're bent, they're broken into tiny fragments. You have to figure out what they looked like before the disaster. You have to reverse engineer the damage. You have to ask yourself, what kind of force caused this fracture? What kind of temperature caused this discoloration? What kind of pressure caused this deformation? Let me give you an example. In 1998, a gas pipeline in Australia exploded. The blast was massive. It created a crater almost 100 feet wide. It destroyed a nearby house. It killed a family of 4. The investigators had to figure out what caused the explosion. They started by examining the pipeline itself. They found a small crack in the pipe. The crack was about 1 inch long. It was caused by a tiny flaw in the welding process. The flaw had been there for years, slowly growing, waiting for the right conditions to fail. The investigators then looked at the history of the pipeline. They found that the pressure in the pipe had been fluctuating. It had been going up and down, stressing the metal, making the crack grow. And then, on the day of the explosion, the pressure had spiked. The crack had opened, the gas had escaped, and the explosion had happened. But the investigators didn't stop there. They wanted to know why the pressure had spiked. They discovered that the control system had a bug. It was supposed to maintain a constant pressure, but a software error was causing it to fluctuate. And then, on that fateful day, a maintenance crew had made a mistake. They had left a valve open. The pressure had spiked, and the pipeline had failed. Each piece of the puzzle led to another piece. The crack led to the welding flaw. The welding flaw led to the pressure fluctuations. The pressure fluctuations led to the software bug. The software bug led to the maintenance error. And the maintenance error led to the explosion. This is the cascade effect we talked about in the last chapter. A series of small failures, each one individually insignificant, that combined to create a catastrophe. The investigators had to trace the entire chain. They had to understand how each failure led to the next. They had to reconstruct the entire story from a pile of debris. Now, let me show you how this works in a more famous case. The collapse of the Hyatt Regency walkways in 1981. Remember that one? 114 people died when 2 skywalks fell onto a tea dance in a Kansas City hotel. The forensic engineers who investigated that disaster started by looking at the walkways themselves. They found that the connection between the walkway and the steel rods was completely inadequate. The nuts that were supposed to hold the walkway in place had sheared off. They had been asked to carry a load that was twice what they were designed for. The investigators then looked at the design drawings. They found that the original design had been different. The walkways were supposed to be supported by a single long rod that passed through the second-level walkway without bearing any weight. But the contractors had changed the design to make construction easier. Instead of 1 rod, they used 2 rods. 1 rod connected the 4th-level walkway to the 2nd-level walkway, The other rod connected the second-level walkway to the ceiling. This change, seemingly simple, had doubled the load on the nuts that supported the second-level walkway. Instead of just supporting the second-level walkway, they were now supporting both walkways. The nuts couldn't handle the load. They sheared off. The walkways fell. The investigators asked why the change had been made. They discovered that the original design had been rejected by the contractors because it was too hard to assemble. The contractors had proposed a change that made the construction easier. The change was approved without anyone checking the engineering. The investigators asked why the change was approved. They discovered that the person who approved the change was not an engineer. He was a supervisor who didn't understand the design. He assumed that the change was harmless. He was wrong. And the investigators asked why the change wasn't reviewed. They discovered that there was no review process in place. The contractors were responsible for their own work. There was no independent oversight. And so, a fatal flaw was built into the walkways. This is the power of forensic engineering. It takes a disaster and breaks it down into its component parts. It shows you exactly where things went wrong, and it provides a roadmap for preventing future disasters. After the Hyatt Regency collapse, the engineering profession was shaken. The American Society of Civil Engineers created new standards for the review of structural designs. They created new requirements for the training of engineers. They created new rules for the approval of design changes. And every one of those changes can be traced back to a forensic investigation. Every one of those changes was inspired by the analysis of a disaster. But forensic engineering isn't just about preventing future disasters. It's also about understanding the limits of our knowledge. It's about recognizing that we don't know everything. It's about being humble in the face of complexity. Take the Tacoma Narrows Bridge collapse in 1940. The forensic engineers who investigated that disaster had to figure out why the bridge fell. They knew it was caused by wind, but they didn't understand exactly how the wind had made the bridge fall. So they built models. They studied the aerodynamics of the bridge. They ran tests. And they discovered a phenomenon called aeroelastic flutter. It happens when the wind causes the bridge to twist at its natural frequency.
The twisting creates a feedback loop. The wind makes the bridge twist. The twisting creates a new shape. The new shape changes how the wind hits the bridge, and the bridge twists even more. Before 1940, no one knew this could happen. No one had ever seen a bridge literally twist itself to pieces in a moderate wind. But after the disaster, engineers knew. They understood the phenomenon. They could design bridges to resist it. And that's the real power of forensic engineering. It turns a tragedy into a lesson. It takes something that went horribly wrong and uses it to make the world better. Now, let me show you how this process works in the modern world. In 2013, the Deepwater Horizon oil spill was investigated by a team of forensic engineers. They had to figure out why the blowout preventer failed. Why did the system that was supposed to stop the oil from leaking fail? They started by examining the blowout preventer itself. They found that it had been damaged. The damage was caused by a piece of the drill pipe that had bent during the blowout. The damaged blowout preventer couldn't seal the well. The oil continued to flow. The disaster continued. The investigators then looked at the history of the blowout preventer. They found that it was poorly maintained. The maintenance logs showed that it had been inspected but not properly serviced. The people who were supposed to check it had made mistakes. They had overlooked the damage. The investigators asked why the maintenance was poor. They found that the crew was understaffed. The company was trying to save money. They had cut corners on maintenance. They had assumed that the blowout preventer would work when it was needed. But the forensic engineers didn't stop there. They also examined the well design. They discovered that the casing, the steel pipe that lined the well, was not properly cemented. There was a gap between the casing and the rock. That gap allowed the oil to escape. The investigators asked why the cementing was poor. They found that the cementing operation was rushed. The crew was under pressure to finish quickly. They had cut corners. They had assumed that the cement would work. Each piece of the puzzle led to another piece. The blowout preventer failure led to the maintenance failure. The maintenance failure led to the staffing failure. The cementing failure led to the design failure. The design failure led to the industry failure. And all of these failures combined to create the largest environmental disaster in American history. 11 people died. Thousands of miles of coastline were affected. Billions of dollars were spent on cleanup. The forensic engineers had to understand every piece of that puzzle. They had to reconstruct the entire story from a pile of debris. And they did. They produced a report that was thousands of pages long. It identified the mistakes. It recommended changes. It made the industry safer. That's the beauty of forensic engineering. It takes the worst that the world can offer and turns it into the best. It takes tragedy and transforms it into progress. Anthony Safronas writes that forensic engineering is about asking the right questions. Not just what happened, but why did it happen? And how can we prevent it from happening again? It's about being humble enough to admit that we don't know everything. It's about being curious enough to keep asking questions. And it's about being brave enough to face the answers, even when they're uncomfortable. There's a concept in engineering that keeps engineers awake at night. It's called the cascade of inevitability. It's the moment when a series of small, seemingly insignificant events align in just the wrong way, and everything begins to unravel. It's like watching a line of dominoes fall, one after another, and knowing that there's absolutely nothing you can do to stop it. The cascade is terrifying because it's so ordinary. Each step along the way seems harmless. Each decision seems reasonable. Each mistake seems minor. But together they form an unbreakable chain of disaster. Let's look at a classic example. The Sansina disaster, which I mentioned briefly in the first chapter. On December 17, 1976, the Sansina, a Liberian oil tanker, was sitting at the port of Los Angeles in San Pedro, California. The ship had just unloaded 212,000 barrels of Indonesian crude oil. The crew was doing what crews always do after unloading. They were filling the empty cargo tanks with seawater. It's called ballasting. It keeps the ship stable on its return voyage. Standard procedure. Nothing unusual, nothing to worry about. But on that particular day, the ballasting created a problem. The seawater forced the remaining oil fumes out of the tanks and onto the deck. Those fumes, heavier than air, started pooling on the deck. They couldn't dissipate. The air was still. No wind to blow them away. Standard weather, nothing unusual, nothing to worry about. But then the fumes found an ignition source. A spark from a piece of equipment, a hot surface, something. Nobody knows exactly what. But it happened. The fumes ignited. The explosion was massive. The ship was torn apart. 9 people died, dozens were injured. The blast was felt 40 miles away. What made the Sansina disaster so tragic was that it was entirely preventable. If the ship had had an inert gas system to prevent the fumes from becoming flammable, if the ventilation system had been working properly, if the crew had been more careful. Any one of those things could have stopped the cascade, but they didn't. The investigation revealed a troubling truth. The ship's safety systems were inadequate. The flame screens that were supposed to prevent fires from reaching the tanks were missing. The gas lines that were supposed to carry away fumes were rusted. The crew had become complacent. They'd been doing this for so long that they'd forgotten the dangers. This is the cascade of inevitability. It starts with a small problem, a rusted pipe, a missing screen, a complacent crew. Each problem seems minor, but they combine.
They reinforce each other, and eventually they create a disaster that seems inevitable in hindsight. Now let's jump forward to 1973, March 2nd to be exact. A Fairfax County, Virginia apartment complex called Skyline Plaza was nearing completion. It was a massive project. 4 structures, each 24 stories tall. Hundreds of apartments, thousands of workers. On that day, workers were pouring concrete on the 24th floor. At the same time, other workers were removing the wooden forms that supported the concrete columns on the 22nd floor. This was standard practice. Pour the concrete, let it cure, remove the forms, build the next floor. But on this day, the concrete on the 22nd floor hadn't cured properly. It was still too weak to support the weight above. The forms were removed too early. The columns couldn't hold the load. One of the structures collapsed. 14 workers died. The investigation revealed a cascade of failures. The contractor was in a hurry. They wanted to finish the project on time. They were pushing their workers to work faster. They didn't check the concrete. They assumed it was ready. They were wrong. But the cascade didn't stop there. The building inspectors hadn't been doing their job. They were supposed to check the concrete's strength before allowing construction to continue. They didn't. They assumed the contractor was following the rules. They were wrong. And the engineers who designed the building, they had included instructions about how long the forms should stay in place. But those instructions were ignored.
The construction manager assumed the workers knew what they were doing. The workers assumed the forms were safe. Everyone assumed. Everyone was wrong. The cascade is always the same. A series of assumptions, a series of shortcuts, a series of small mistakes. Each one, by itself, is survivable. But together, they create a catastrophe. Now let me tell you about a more modern cascade. In 2014, the French railway company SNCF ordered 2,000 new trains at a cost of over $20 billion. They were state-of-the-art, high-speed, comfortable, the future of French rail. But there was a problem. The trains were too wide. The old train stations, the ones built more than 30 years ago, had platforms that were too narrow. The new trains couldn't fit. They would scrape against the platforms, they would derail, they would cause accidents. How did this happen? The investigation revealed a cascade of failures.
The engineers who designed the trains were given the wrong specifications. They were told the platforms were a certain width. They designed the trains accordingly. But the specifications were wrong. The data hadn't been updated. The old stations had been measured decades ago. They were measured using outdated methods. The engineers didn't double-check. They assumed the data was correct. They had too much work. They were under pressure to deliver on time. They didn't have time to verify. They trusted the data. They were wrong. The cascade continued. The managers who approved the design didn't review it carefully. They assumed the engineers had done their job. They had other things to worry about. They signed off. They were wrong. The result? Over 1,000 platforms had to be modified. Each modification cost tens of thousands of dollars. The total cost was over $100 million. And the trains were delayed by years. All because of a measurement error.
All because of a cascade of assumptions. Now, let me share another example, one that's less technical but just as revealing. In 2008, the Dubai Mall's aquarium, one of the largest in the world, began to leak. Water seeped through a crack between 2 panels. The mall was evacuated. The aquariums were closed. The repairs took hours. The lost revenue was millions. What caused the crack? The investigation revealed a cascade of failures. The panels weren't sealed properly. The seals were damaged during installation. The workers who installed them were under pressure. They had to finish quickly. They cut corners. They assumed the seals would hold. They were wrong. The managers who approved the installation didn't check the seals. They assumed the workers had done a good job. They were under pressure to open the mall on time. They signed off. They were wrong. The engineers who designed the aquarium didn't account for the pressure of the water.
They assumed the seals would be installed correctly. They didn't create enough redundancy. They didn't build backup systems. They assumed. They were wrong. The cascade is the same everywhere. A series of small failures. A series of assumptions. A series of shortcuts. Each one by itself is survivable, but together they create a catastrophe. Now, let me ask you something. Why do we keep making these mistakes? Why do we keep assuming that things will work out? Why do we keep cutting corners and ignoring the risks? The answer lies in human nature. We're optimists. We believe that things will work out. We believe that we're good enough. We believe that we're lucky. And most of the time, we're right. Most of the time, things do work out. Most of the time, our assumptions are correct. Most of the time, our shortcuts don't cause any harm. But the cascade doesn't need all the mistakes to happen at once. It just needs enough of them. It just needs the right combination. And when that combination occurs, the result is catastrophic. Henry Petrosky, in his book To Engineer is Human, argues that the most dangerous period for a technology is when it's new, when it's untested, when people don't fully understand how it works. In those early days, failures are common. The technology is improved, the bugs are worked out. Eventually, it becomes reliable. And that's when the next danger arises: complacency. When a technology becomes reliable, people start to take it for granted. They stop paying attention. They stop being careful. They stop questioning assumptions. They assume it will work. They assume everything is fine. And that's when the cascade begins. When people stop questioning. When people stop caring. When people stop looking for the small mistakes that can combine into a catastrophe. The Sansina, Skyline Plaza, SNCF, the Dubai Aquarium. Each of these disasters was caused by complacency. Each was caused by a cascade of assumptions.
Each was preventable. But each happened because people stopped paying attention. This is the lesson of the cascade. The disasters aren't caused by one big mistake. They're caused by dozens of small mistakes. They're caused by a culture that doesn't value safety. They're caused by people who assume that someone else is checking. The good news is that the cascade can be broken. Each link in the chain is an opportunity to stop the disaster. If someone had checked the flame screens on the Sansina, if someone had tested the concrete at Skyline Plaza, if someone had measured the platforms at SNCF, if someone had inspected the seals at the Dubai Aquarium, each of those actions would have broken the chain. Each of those actions would have prevented the disaster. But they didn't happen. Because people assumed. Because people were in a hurry. Because people were complacent. That's the bad news. And it's the reason we keep making the same mistakes. We're human. We're fallible. We assume. We cut corners. We make mistakes. But we can do better. We can pay attention. We can question assumptions. We can check the small things. We can break the cascade before it starts. There's a moment in every major engineering investigation when the investigators realize something uncomfortable. It's the moment when they stop looking at the machines and start looking at the people. Because the truth is, most engineering disasters aren't caused by equipment failure. They're caused by human failure. Smart people making what, in hindsight, seem like incredibly stupid decisions. Let me tell you about a classic case. On January 28, 1986, the Space Shuttle Challenger lifted off from Cape Canaveral, Florida. 73 seconds later, it broke apart in mid-air. 7 astronauts died. The investigation that followed was one of the most thorough in history.
The immediate cause was a failure of the O-rings, the rubber seals that prevented hot gases from escaping the solid rocket boosters. The O-rings had failed because the temperature at launch was much colder than any previous launch. The rubber had become too stiff to seal properly. But that wasn't the real story. The real story was what happened in the days leading up to the launch. Engineers at Morton Thiokol, the company that built the boosters, had discovered the O-ring problem years earlier. They had tested the rings at cold temperatures and found that they became brittle. They had warned their managers. They had recommended that the shuttle not be launched in temperatures below 53 degrees Fahrenheit. On the night before the launch, those engineers held an urgent conference call with NASA. They made their case. They showed their data. They recommended delaying the launch. They were right, and they were overruled. How did that happen? How could experienced engineers, the best in the world, be ignored by their own managers? The answer lies in something psychologists call groupthink. When a group of people are under pressure to reach a decision, they tend to suppress their doubts. They don't want to rock the boat. They don't want to be the one who delays the launch. They don't want to be seen as difficult. At NASA, there was a culture of go fever. The agency was under enormous pressure to keep the shuttle program on schedule. Delays cost money. Delays cost political support. Delays cost jobs. The managers didn't want to hear bad news. They wanted to hear that everything was fine. The engineers knew the truth. But they were under pressure to agree. The managers wanted a consensus. They wanted everyone to be on board. So the engineers went along. They suppressed their doubts. They agreed to the launch. And 7 people died. This is what we call the human factor. It's not about incompetence. It's about psychology. It's about the way our brains work under pressure. It's about the tendency to agree with the group, the tendency to ignore our own doubts, the tendency to convince ourselves that everything will be fine. Let me give you another example. In 1977, 2 Boeing 747s collided on a runway in Tenerife, Spain. 583 people died. It was the deadliest aviation accident in history. The immediate cause was a miscommunication between the captain of one of the planes and the air traffic controller. The captain thought he had clearance to take off. The controller thought he was telling him to wait. They were using the same words, but they meant different things. It was a simple misunderstanding, a tiny error, and it killed nearly 600 people. But why did the captain misinterpret what the controller said? Why didn't he ask for clarification? The answer, again, is the human factor. The captain was under pressure. His plane was running late. The airport was foggy. Visibility was poor. He was trying to get out quickly. He heard what he wanted to hear. He assumed the controller had given him clearance. He was wrong. This is a pattern we see again and again. A skilled, experienced professional makes a simple error. The error has devastating consequences. And the reason for the error is always the same: stress, pressure, fatigue, complacency. Think about the pilots of the Tenerife disaster. They were at the top of their profession. They had thousands of hours of flight time.
They had survived countless emergencies. They knew what to do in a crisis. But in that foggy airport, under the pressure of a delayed flight, they made a mistake. Now, I want to tell you about a lesser-known case. In 1991, a fire broke out at the Imperial Foods processing plant in Hamlet, North Carolina. 25 people died. The cause of the fire? A simple equipment failure, a faulty conveyor belt.
A spark that ignited some chicken fat. But the real cause of the deaths was something else. The plant had been built with no fire suppression system, no sprinklers, no fire alarms, no emergency exits. The workers were trapped. They couldn't escape. They died where they worked. Why was the plant built without fire safety systems? The answer, once again, is the human factor. The owner of the plant was trying to save money. He had cut corners on construction. He had avoided the expense of installing fire suppression systems. He assumed nothing would happen. He assumed he was saving money. He was wrong. And 25 people paid for his mistake. Now, let me give you a more recent example. In 2020, the Boeing 737 MAX disaster was caused, in part, by the human factor. The plane had a software system called MCAS that was designed to prevent stalls. But the system was flawed. It could override the pilot's controls. It could push the plane's nose down, even when the pilot was trying to pull up. The engineers who designed MCAS knew it had the potential to cause problems. They knew it could put the plane in dangerous situations. But they didn't tell anyone. They didn't tell the pilots. They didn't tell the regulators. They didn't tell the airlines. They assumed the problem would be fixed before anyone noticed. They were wrong, and 346 people died. Why didn't the engineers speak up? Why didn't they raise the alarm? The answer, again, is the human factor. They were under pressure to deliver. They were trying to keep costs down. They didn't want to be the ones who delayed the plane's certification. They didn't want to be seen as difficult. They stayed quiet. They assumed someone else would catch the problem. They were wrong. This is a pattern we've seen throughout this story. The engineers are the experts. They know the truth. But they don't speak up.
They don't challenge the assumptions. They don't question the decisions. They go along. They agree. They assume. And then the disaster happens. Why do we do this? Why do we suppress our doubts? Why do we agree when we know we're wrong? The answer is rooted in our biology. Our brains are wired to avoid conflict. We're social animals. We want to get along. We want to be liked. We want to be part of the group. When we're under pressure to agree, we tend to go along. We don't want to be the one who stands out. We don't want to be the one who says no. This is called the abnormal norm effect. When a group of people are under pressure, they tend to adopt a shared view of reality. They suppress their doubts. They convince themselves that everything is fine. They create a shared delusion. In the Challenger case, the shared delusion was that the O-rings would work at lower temperatures. The engineers knew they were taking a risk, but they convinced themselves that the risk was acceptable. They convinced themselves that they had tested enough. They convinced themselves that the data was incomplete. They created a story that allowed them to agree. In the Tenerife case, the shared delusion was that the controller had given clearance. The captain heard what he wanted to hear. He convinced himself that everything was fine. He assumed the controller had approved the takeoff. He didn't check. He didn't question. He just went. In the Imperial Foods case, the shared delusion was that nothing would happen. The owner convinced himself that he didn't need fire safety systems. He assumed that the plant would be safe. He convinced himself that the cost of safety was unnecessary. He created a story that allowed him to ignore the risk. In the Boeing case, the shared delusion was that MCAS would work correctly. The engineers convinced themselves that the software was safe. They assumed that the pilots would be able to override it.
They assumed that the regulators would catch any problems. They created a story that allowed them to proceed. The shared delusion is a powerful force. It allows us to ignore the obvious. It allows us to take risks that we wouldn't normally take. It allows us to be wrong. And here's the really scary part. It's not just individuals who are susceptible to shared delusions. It's entire organizations, it's entire industries, it's entire cultures. Look at the nuclear industry after 3 Mile Island. The operators weren't just individuals, they were part of an organization. An organization that had created a culture of denial. A culture that assumed that nuclear power was safe. A culture that ignored the signs of trouble. The organization had created a shared delusion. And that delusion allowed the disaster to happen. Look at the financial industry before the 2008 crash. The bankers weren't just individuals. They were part of an organization.
An organization that had created a culture of risk-taking. A culture that assumed that the markets were safe. A culture that ignored the signs of trouble. The organization had created a shared delusion, and that delusion allowed the crash to happen. The shared delusion is the human factor at its most dangerous. It's the reason we keep making the same mistakes. It's the reason we suppress our doubts. It's the reason we agree when we know we're wrong. So how do we break the cycle? How do we prevent the shared delusion from taking hold? The answer is to create a culture of questioning. A culture where it's safe to speak up. A culture where people are encouraged to challenge assumptions. A culture where the default is not agreement, but skepticism. This is what the aviation industry did after Tenerife. They created a culture of crew resource management. Pilots are trained to communicate clearly. They're trained to challenge each other. They're trained to avoid the shared delusion.
As a result, aviation has become one of the safest forms of transportation in the world.
This is what the nuclear industry did after 3 Mile Island. They created a culture of transparency. They created independent oversight. They created rigorous training programs. As a result, nuclear accidents have become increasingly rare. This is what we need to do in every industry. We need to create a culture that values safety over speed. A culture that encourages questioning. A culture that doesn't punish people for speaking up. A culture that recognizes the human factor and works to mitigate it. Because the human factor isn't going away. We're human. We make mistakes. We suppress our doubts. We agree when we know we're wrong. It's part of who we are. But we can do better. We can recognize our weaknesses and build systems that compensate for them. We can create cultures that value safety over speed. We can encourage questioning. We can challenge assumptions. We can break the cycle. And that's the point of this story. Not to scare you, not to make you cynical, but to show you that we can be better. We can learn from our mistakes. We can create a world where the human factor doesn't lead to disaster. We can build systems that are resilient, even in the face of human error. There's a phrase you'll hear in engineering circles. It's a bit grim, but it captures something important. The regulations are written in blood. Every safety standard, every building code, every inspection requirement exists because someone died. Someone's life was lost because the previous standard wasn't good enough. And that loss forced the industry to change. This is the turning point. The moment when a tragedy becomes a catalyst for progress. When the pain of a disaster becomes the motivation for change. It's the most powerful force in engineering. And it's the only way we've ever made real progress in safety. Let me tell you about one of the most famous turning points in history. December 3rd, 1984. Bhopal, India. A chemical plant owned by Union Carbide released a cloud of toxic gas, methyl isocyanate. It drifted over the city. Thousands died. Hundreds of thousands were injured. It was the worst industrial disaster in history. In the aftermath, the world was horrified. How could this have happened? How could a chemical plant release so much poison that it could kill so many people? The investigation revealed a cascade of failures. The plant was poorly maintained. The safety systems were broken or deactivated. The operators were poorly trained. The company had cut corners to save money, and when the gas started leaking, no one knew what to do. But the investigation also revealed something else, something that made the disaster even more tragic. The company had known about the risks. They had been warned. Years earlier, a safety audit had found serious problems at the plant. The report was buried. The problems were ignored.
And then the disaster happened. The Bhopal disaster was a turning point. It led to the creation of new laws and regulations around the world. In the United States, the Emergency Planning and Community Right to Know Act was passed in 1986. It required companies to disclose what chemicals they were using. It required them to have emergency response plans. It required them to be transparent about the risks they were creating. In Europe, the Seveso Directive was updated and expanded. Named after a 1976 disaster in Italy, where a chemical plant exploded and released dioxin, the directive established strict safety requirements for industrial facilities. It required companies to identify the risks they were creating. It required them to have plans for dealing with accidents. It required them to be accountable for their actions. These regulations didn't exist before Bhopal. They were written because of Bhopal. They were written in the blood of the dead. Now, let me tell you about another turning point. October 15th, 1994. Seoul, South Korea. The Seongsu Bridge, a major thoroughfare, collapsed during rush hour. A section of the bridge fell into the Han River. 32 people died. 17 were injured. The bridge was less than 15 years old. It was supposed to last decades. The investigation revealed a cascade of failures. The bridge had been built with a faulty weld. The weld had been compromised during construction. The inspectors who should have caught the problem had been negligent. They had approved the weld without properly checking it. And then, on that October morning, the weld gave way. The bridge collapsed. People died. But the turning point came after the investigation. The Korean government was deeply shaken. How could a bridge that was supposed to be safe fail so catastrophically? How could such an obvious flaw have gone undetected? The government commissioned a full review. They discovered that the problem wasn't just the bridge. The problem was the entire system. The inspections were inadequate. The standards were insufficient. The training was poor. The entire system was broken. So they changed it. They rewrote the building codes. They created new inspection standards. They required better training for inspectors. They made sure that what happened on the Seongsu Bridge would never happen again. But they didn't stop there. They also demolished the rest of the bridge and rebuilt it from scratch. They wanted to send a message. They wanted to show the world that they took safety seriously. They wanted to ensure that no one would ever forget what had happened. The cost was enormous. Hundreds of millions of dollars. But the message was clear. We will not tolerate this. We will not let this happen again. Now, let me tell you about a more recent turning point. August 29th, 2005, Hurricane Katrina hits the Gulf Coast of the United States. The storm surge overwhelms the levee system in New Orleans. The city floods. More than 1,800 people die. Hundreds of thousands are displaced. It's one of the worst natural disasters in American history. But the levee failure wasn't just a natural disaster. It was an engineering disaster. The levees were designed to withstand a storm of a certain intensity. Katrina was stronger than that. But it wasn't just the storm, it was the design. The levees had flaws. They were built on weak soil. They weren't deep enough. They weren't strong enough. And when the storm surge hit, they failed. The investigation revealed a cascade of failures. The US Army Corps of Engineers, the agency responsible for the levees, had known about the risks. They had known that the levees were inadequate, but they hadn't fixed them. The funding was cut. The priorities were elsewhere. And then the hurricane came.
The turning point came after the disaster. The Corps of Engineers was forced to take responsibility. New standards were created. New funding was allocated. New levees were built. And the disaster became a lesson. It became a warning. We must do better. But the turning point wasn't just about the levees. It was also about the response. The government's response to the disaster was widely criticized. Emergency services were slow. Communication was poor. Help arrived late. People died who could have been saved. So the government changed. They reorganized the emergency management system. They created new protocols. They improved communication. They made sure the lessons of Katrina were learned. They made sure it wouldn't happen again. Now, let me give you a more obscure but equally telling example. In 2014, the French railway company SNCF ordered 2,000 new trains. They were supposed to be the future of French rail. But then the discovery was made.
The trains were too wide for the old stations. Over 1,000 platforms had to be modified. The cost was enormous. The delays were painful. The turning point in this case was more bureaucratic, but no less significant. The SNCF realized that their data was out of date. They had been using measurements taken decades ago. They had never updated them. So they changed their process. Now, they verify all their data. They don't assume anything. They check everything. The lesson was learned. The system was improved. What connects all these turning points? What makes a disaster become a catalyst for change? First, the disaster must be visible. It must be undeniable. No one can ignore it. No one can pretend it didn't happen. The Bhopal disaster was impossible to ignore. Thousands died. The Seongsu Bridge collapse was impossible to ignore. The bridge fell into a river. Hurricane Katrina was impossible to ignore. The city flooded. The SNCF train problem was impossible to ignore. The trains couldn't fit. Second, the disaster must be investigated. There must be a thorough examination of what happened. The investigation must be independent. It must be transparent. It must be honest. In Bhopal, the investigation was exhaustive. In Seongsu, it was comprehensive. In Katrina, it was definitive. In the SNCF case, it was thorough. The investigations led to findings. The findings led to recommendations. The recommendations led to change. Third, the investigation must lead to accountability. Someone must be held responsible. Someone must be punished. Someone must be forced to change. In Bhopal, the company was held liable. In Seongsu, the inspectors were prosecuted. In Katrina, the Corps of Engineers was forced to admit fault. In the SNCF case, the organization was forced to change its procedures. Fourth,
And most importantly, the lessons must be applied. The disaster must become a lesson for the future. The new standards must be adopted. The new procedures must be implemented. The new attitudes must be embraced. In every one of these cases, the lessons were applied, the standards were improved, the procedures were updated, the attitudes were changed. This is how progress happens. It happens through pain. It happens through loss. It happens through tragedy. The regulations are written in blood because there's no other way to get people to listen. There's no other way to force change. There's no other way to make sure that the mistakes of the past aren't repeated. But here's the thing. The progress doesn't have to be so painful. We can learn from the disasters of others. We can apply the lessons without having to experience the tragedy ourselves. This is why the investigations are so important. They create a public record. They create a body of knowledge. They create a set of lessons that can be applied by anyone. This is what forensic engineering is all about. It's not just about understanding what happened. It's about making sure it doesn't happen again. It's about taking the disaster and using it to improve the system. It's about turning tragedy into progress. So when you see a disaster on the news, don't just see the tragedy, see the turning point. See the opportunity for change. See the possibility for progress. Because that's what makes our world better. That's what makes our systems safer. That's what engineering is all about. If you've been paying attention to this story, you might have noticed a pattern. Something that repeats itself across every disaster we've discussed. The same mistakes, the same assumptions, the same cascading failures. It's almost as if we're doomed to repeat the same errors, no matter how much we learn. Let me walk you through what I mean. Take the Hyatt Regency walkway collapse. The engineers made a change to the design to simplify construction. They didn't recalculate the loads. They assumed everything would be fine. They were wrong. Now, take the Boeing 737 MAX disaster. The engineers made a change to the software to improve performance. They didn't fully test the system. They assumed everything would be fine. They were wrong. Now take the SNCF train problem. The engineers assumed that the old platform measurements were still accurate. They didn't verify the data. They assumed everything would be fine. They were wrong. Now take the Sansina explosion. The crew assumed that the ballasting procedure was safe. They didn't check the ventilation. They assumed everything would be fine. They were wrong. Do you see it? The pattern is the same. Someone assumes something. They don't check. They assume they're right, and they're wrong. This is the anatomy of failure. It's a set of recurring themes that appear in almost every engineering disaster. Understanding these themes is the key to preventing future disasters. The first theme is overconfidence. We believe we're smarter than the problem. We believe we've accounted for everything. We believe that our design is perfect. This is a dangerous mindset. It leads to complacency. It leads to cutting corners. It leads to ignoring warnings. It leads to disaster. Think about the engineers who designed the Hyatt Regency walkways. They were confident in their abilities. They were confident in their design. They didn't think they needed to double-check the loads. They were overconfident, and people died. Think about the engineers who designed the Boeing 737 MAX. They were confident in their software. They were confident in their system. They didn't think they needed to fully test it. They were overconfident, and people died. Overconfidence is a natural human trait. We all believe we're above average. We all believe we're smarter than the next person. But in engineering, overconfidence is deadly. It blinds us to our own mistakes. It makes us ignore the warning signs. The second theme is complexity. Our systems are becoming more and more complex. And the more complex a system is, the harder it is to understand. The harder it is to predict. The harder it is to control. Think about the 3 Mile Island nuclear plant.
The cooling system was incredibly complex. The operators couldn't understand what was happening. They couldn't interpret the instruments. They couldn't see the big picture. The complexity of the system overwhelmed them. Think about the CrowdStrike disaster. The software was incredibly complex. The engineers couldn't understand all the interactions. They couldn't predict how the update would behave. The complexity of the system overwhelmed them. Complexity is a double-edged sword. It allows us to do amazing things. It allows us to build systems that are smarter and more capable than ever before. But it also creates new vulnerabilities, new ways to fail, new paths to disaster. The third theme is complacency.
When a system has been working for a while, we start to assume it will keep working. We stop paying attention. We stop being careful. We stop asking questions. Think about the Sansina explosion. The crew had done the ballasting procedure 1,000 times before. They were complacent. They assumed everything was fine. They didn't check the ventilation. They didn't notice the missing flame screens. They were complacent. And the ship exploded. Think about the Imperial Foods plant fire. The owner had been cutting corners for years. Nothing had happened. He was complacent. He assumed nothing would happen. He didn't install fire safety systems. He didn't provide emergency exits. He was complacent. And 25 people died. Complacency is the enemy of safety. It's the reason we keep making the same mistakes. It's the reason we ignore the warnings. It's the reason we don't prepare for the worst. The fourth theme is the pressure to cut corners.
In every disaster we've discussed, there was pressure to save money, pressure to save time, pressure to make the project work on schedule. Think about the Space Shuttle Challenger. The managers were under pressure to keep the launch on schedule. They didn't want to delay. They didn't want to look weak. They ignored the warnings. They cut corners. And 7 people died. Think about the Deepwater Horizon. The engineers were under pressure to complete the well on time. They didn't want to delay. They didn't want to look incompetent. They ignored the warning signs. They cut corners. And 11 people died. The pressure to cut corners is always present. It's a fact of life. But when it becomes more important than safety, disaster follows. The fifth theme is the breakdown of communication. In every disaster we've discussed, there was a failure to communicate. Someone knew something. Someone didn't tell someone else. The information didn't get where it needed to go.
Think about the Hyatt Regency walkways. The engineer who changed the design didn't tell the engineers who did the calculations. The contractors didn't tell the architects. The information didn't flow. The failure was built in. Think about the Boeing 737 MAX. The engineers who designed the MCAS system didn't tell the pilots about it. The pilots didn't know what to do when it malfunctioned. The information didn't flow. The failure was built in. Communication is the lifeblood of engineering. When it breaks down, disaster follows. The sixth theme is the failure of oversight. Someone was supposed to be checking. Someone was supposed to be verifying. Someone was supposed to be catching mistakes. And they didn't. Think about the Seongsu Bridge collapse. The inspectors were supposed to be checking the welds. They didn't do their job. They approved the faulty work. The oversight failed, and the bridge collapsed. Think about the Skyline Plaza collapse. The building inspectors were supposed to be checking the concrete. They didn't do their job. They approved the unsafe work. The oversight failed, and the building collapsed. Oversight is essential. It's the safety net. It's the last line of defense. When it fails, disaster follows. The seventh theme is the failure to learn. In every disaster we've discussed, the lessons were available. Someone had warned about the risks, someone had pointed out the problems, and no one listened. Think about the Challenger disaster. The engineers at Morton Thiokol had warned about the O-rings years earlier. They had data, they had evidence, and no one listened. The warnings were ignored. The disaster happened. Think about the Deepwater Horizon. The engineers had warned about the risks of deepwater drilling. They had data, they had evidence, and no one listened. The warnings were ignored. The disaster happened. Learning is the most important skill in engineering.
When we fail to learn, we doom ourselves to repeat the mistakes of the past. The eighth theme is the illusion of safety. We believe that our systems are safer than they really are. We believe that the safeguards are working. We believe that the protections are adequate. And we're wrong. Think about the Fukushima nuclear disaster. The plant was designed to withstand a tsunami. The safety systems were supposed to work. The backup generators were supposed to kick in, and they didn't. The illusion of safety was shattered. Think about the Boeing 737 MAX. The pilots believed the plane was safe. The regulators believed the plane was safe. The airlines believed the plane was safe. And it wasn't. The illusion of safety was shattered. The illusion of safety is dangerous. It makes us complacent. It makes us stop looking. It makes us assume everything is fine. And when the disaster happens, we're shocked. We can't believe it happened. We didn't see it coming.
The ninth theme is the cascade effect.
We've talked about this before. When one failure leads to another, which leads to another, creating a chain reaction that brings the whole system down. Think about the 3 Mile Island accident. The pump failed. The cooling system shut down. The operators misinterpreted the instruments. They turned off the backup cooling. The reactor overheated. The fuel melted. The cascade was complete. Think about the Optus network crash. The software update had a bug. The routers started rerouting traffic incorrectly. The network became unstable. The routers crashed. The whole network went down. The cascade was complete. The cascade effect is the most dangerous form of failure. It turns a small problem into a catastrophe. It turns a simple mistake into a disaster. The 10th theme is the human factor. We've talked about this at length. The psychology of engineering. The way our brains work against us. The tendency to agree with the group.
The tendency to ignore our own doubts. The tendency to assume everything will be fine. The human factor is the most persistent theme in engineering disasters. It's the one thing that never changes. We're human. We make mistakes. We're fallible. And no matter how much technology advances, the human factor remains. So what do we do about all of this? How do we break the pattern? How do we stop making the same mistakes? First, we have to recognize the pattern. We have to see it. We have to understand it. We have to acknowledge that we're susceptible to it. That's the first step. Second, we have to build systems that compensate for our weaknesses. We have to create redundancies. We have to create backups. We have to create independent checks. We have to make it harder for a single mistake to bring everything down. Third, we have to create a culture of safety. A culture where people are encouraged to speak up. A culture where warnings are taken seriously.
A culture where cutting corners is not acceptable. A culture where safety comes first. Fourth, we have to keep learning. We have to study the disasters. We have to analyze the failures. We have to apply the lessons. We have to keep getting better. The pattern will never completely disappear. We're human. We'll always make mistakes. But we can reduce the frequency. We can reduce the severity. We can make the disasters smaller. We can make them less deadly. And that's the goal. Not perfection, but progress. Not eliminating failure, but learning from it. Not creating a world without disasters, but creating a world where disasters are less frequent, less severe, and more survivable. We've traveled through decades of disasters. We've seen bridges collapse, buildings crumble, ships explode, and systems fail. We've traced the cascades, analyzed the human factors, and learned lessons. But here's the thing, we're not done. The future holds new challenges, new systems, new ways to fail,
and we're not ready for all of them. Let me start with something that's happening right now. Artificial intelligence, machine learning, autonomous systems. These are the technologies of tomorrow, and they're already here. Self-driving cars, AI-powered medical diagnosis, automated financial trading, smart cities managed by algorithms. These systems are incredibly powerful. They can process more information than any human. They can make decisions faster than any human. They can operate around the clock without fatigue. But they also have weaknesses. And we don't fully understand all of them. Take self-driving cars. The promise is simple. Computers don't get distracted. They don't get tired. They don't make the same mistakes as human drivers. But they also don't understand context the way humans do. They don't understand social cues. They don't understand the subtle signals that humans use to communicate.
In 2018, an Uber self-driving car struck and killed a pedestrian in Arizona. The car's sensors had detected the pedestrian, but the software classified her as a false positive. It didn't recognize her as a human. It didn't brake. It didn't swerve. It just hit her. The investigation revealed a cascade of failures. The software had been trained on data that didn't include enough nighttime pedestrian scenarios. The safety driver was distracted, watching a television show on her phone. The car's emergency braking system had been disabled to prevent sudden stops during testing. The cascade was complete. A woman was dead. Now, think about the implications. Self-driving cars are going to become more common. They're going to be on the roads with us, and they're going to make mistakes. They're going to misunderstand situations. They're going to fail in ways we haven't anticipated. And we're going to have to learn from those failures. The question is, will we learn? Will we treat each accident as a lesson? Will we improve the systems? Or will we repeat the mistakes of the past? Now consider another emerging technology: artificial intelligence in medicine. AI systems are being used to diagnose diseases, to recommend treatments, to predict outcomes. They're incredibly accurate. They can catch things that human doctors miss. But they also have blind spots. In 2019, a study found that an AI system for diagnosing skin cancer was significantly less accurate for people with darker skin. The system had been trained primarily on images of lighter skin. It had learned to associate certain patterns with cancer, but those patterns didn't work the same way for darker skin. The system was biased, and that bias could have deadly consequences. This is a new kind of failure. It's not a structural collapse or a software bug. It's a failure of training data, a failure of representation, a failure to recognize that the data we use to build our systems reflects our own biases and limitations. And it's going to get worse. As AI systems become more powerful, they'll be used in more critical applications. They'll make decisions about who gets a loan, who gets a job, who gets parole. And if those systems are biased, they'll perpetuate and amplify our existing inequalities. This is the future of failure. It's not just about bridges and buildings. It's about algorithms and data. It's about systems that we can't fully understand. It's about machines that make decisions we can't explain. Now, let me talk about another emerging risk: cybersecurity. We've already seen the damage that a single software update can cause. The CrowdStrike disaster was a warning. But the future holds even greater threats. Our critical infrastructure is increasingly connected to the internet. Power grids, water systems, transportation networks, financial systems. They're all linked. They're all vulnerable, and they're all potential targets for attack. In 2021, a cyber attack on the Colonial Pipeline caused a fuel shortage across the eastern United States. Gas stations ran dry, prices spiked. Panic buying set in. It wasn't a physical attack on the pipeline, it was a digital attack. Hackers compromised the billing system and demanded a ransom. The pipeline was shut down as a precaution, but the shutdown caused chaos. People couldn't get to work, goods couldn't be delivered. The economy ground to a halt, all because of a cyber attack on a billing system. This is a new kind of cascade. It's not a physical failure, it's a digital one, but the consequences are just as real. The lights go out, the water stops flowing, the planes stop flying, and we're left wondering how it all happened. Now consider the rise of quantum computing. This is a technology that could revolutionize many fields. It could solve problems that are currently impossible.
It could simulate complex systems. It could discover new materials. But it could also break the encryption that protects our digital world. Most of our online security relies on encryption. Our emails, our bank transactions, our medical records, our government secrets. They're all protected by encryption, and quantum computers could break that encryption. They could read everything. They could steal everything. They could compromise everything. This is a future failure waiting to happen. We know it's coming. We know the threat exists, but we're not fully prepared. We're still developing new encryption methods, but it takes time, and the threat is accelerating. Now let me talk about something even more fundamental: climate change. The changing climate is creating new engineering challenges that we're not fully prepared for. Higher temperatures mean more stress on infrastructure. Bridges expand and contract more. Roads soften and deform. Power lines sag and fail. The Tacoma Narrows Bridge was destroyed by wind. But the future holds even greater threats. Rising sea levels threaten coastal cities. Storm surges are becoming more frequent and more severe. The levees of New Orleans were overwhelmed by Hurricane Katrina. The future holds more of the same. We need to build better defenses. We need to redesign our cities. We need to adapt. But adaptation is expensive. It takes time. It requires political will. And we're not moving fast enough. The disasters are already happening, and they're going to get worse. Now consider the increasing complexity of our systems. We've already seen how complexity can lead to failure. The more interconnected our systems become, the more potential there is for cascading failures. Think about the global supply chain. It's incredibly complex. Goods are manufactured in one country, assembled in another, shipped to a third. The system is efficient. It's also fragile. A disruption in one part of the world can ripple through the entire system. The 2021 Suez Canal blockage is a perfect example. A single ship got stuck. The canal was closed for 6 days. Billions of dollars in trade were disrupted. The global supply chain ground to a halt. All because of one ship. This is the future of failure. It's not just about individual systems. It's about the connections between systems. It's about the interdependencies. It's about the cascades that can spread across the entire globe.
So what do we do about all of this? How do we prepare for failures we can't anticipate? First, we need to invest in resilience. We need to build systems that can withstand failures. Systems that have redundancy. Systems that can degrade gracefully. Systems that can recover quickly. Second, we need to invest in understanding. We need to study these new technologies. We need to understand their vulnerabilities.
We need to develop methods for testing and verification. We need to build the knowledge base. Third, we need to invest in regulation. We need to create rules that ensure safety. We need to require testing. We need to mandate transparency. We need to hold people accountable. Fourth, we need to invest in education. We need to train engineers who understand these new technologies. We need to teach them how to think about failure. We need to prepare them for the challenges of the future. And finally, we need to invest in humility. We need to acknowledge that we don't know everything. We need to be willing to learn. We need to be willing to adapt. We need to be willing to admit when we're wrong. The future of failure is not predetermined. We can shape it. We can influence it. We can make it better. But it requires effort. It requires commitment. It requires a willingness to learn from the past and apply those lessons to the future.
Henry Petrosky wrote that engineering is fundamentally about anticipation, about thinking ahead, about imagining what could go wrong, about preparing for the worst. That's still true. It's more important than ever. So, as we look to the future, let's remember the lessons of the past. Let's remember the bridges that fell, the buildings that crumbled, the ships that exploded, the systems that failed. Let's remember the people who died because we didn't learn fast enough. And let's commit to doing better. Let's commit to building systems that are safe. Let's commit to learning from our mistakes. Let's commit to a future where failures are lessons, not tragedies. So here we are, 10 chapters in. We've travelled through decades of disasters, from the twisting Tacoma Narrows Bridge to the crumbling Hyatt Regency walkways. We've watched the cascade of failures that sank the Sansina and the burst of arrogance that doomed the Challenger.
We've seen how the systems we build to protect us can become the instruments of our destruction. We've traced the human factor, the psychology of groupthink, the pressure to cut corners, the breakdown of communication, the failure of oversight, and the illusion of safety. We've mapped the anatomy of failure. We've identified the recurring themes that connect every engineering disaster. We've looked ahead to the future and the new challenges emerging from artificial intelligence, cybersecurity, quantum computing, and climate change. We've understood that the patterns of failure don't change, they just find new forms. But now we need to answer the most important question of all. What do we do with all of this? How do we take the lessons of the past and apply them to the future? How do we think about failure in a way that helps us prevent it? Henry Petrosky wrote that engineering is fundamentally about anticipating failure. And he's right. But anticipation is not enough.
We also need a framework, a way of thinking, a set of principles that guide our decisions. Here are 10 principles for thinking about failure. They're drawn from every chapter of this story. They represent the accumulated wisdom of generations of engineers who learned through tragedy. This is the most important principle. Assume that your assumptions are wrong. Assume that the data is incomplete. Assume that the system will behave in ways you don't expect. The engineers at SNCF assumed their platform measurements were still accurate. They were wrong. The managers at NASA assumed the O-rings would work at lower temperatures. They were wrong. The crew of the Sansina assumed the ballasting procedure was safe. They were wrong. Assume nothing. Check everything. Verify. Validate. Test. The moment you stop questioning is the moment you start failing. This is the second most important principle. Design your systems so that they fail gracefully. Design them so that a single point of failure doesn't bring everything down. Design them so that they degrade slowly, giving you time to respond. The engineers who designed the Hyatt Regency walkways didn't design for failure. They designed for ease of construction. They designed for speed. They designed for cost. They didn't design for failure. And when the failure came, it was catastrophic. The engineers who designed the Tacoma Narrows Bridge didn't design for failure. They designed for elegance. They designed for lightness. They designed for beauty. They didn't design for failure. And when the wind blew, the bridge twisted itself to pieces. Design for failure. Build redundancy. Create backups. Plan for the worst. Complexity is not your friend, it's your enemy. It creates new vulnerabilities. It creates new paths to failure. It creates new ways for things to go wrong. The 3 Mile Island nuclear plant was a masterpiece of complexity. It had backup systems for its backup systems. It had multiple layers of safety. And it still failed. The operators couldn't understand what was happening. The instruments gave conflicting readings. The system overwhelmed them. The CrowdStrike disaster was a masterpiece of complexity. The software was incredibly sophisticated. It was designed to catch threats that other systems missed. And it still failed. A tiny bug in a configuration file brought down millions of computers. Respect complexity. Don't add it unless you absolutely need it. And when you add it, understand it. Test it. Verify it. This is the principle that engineers most often ignore. The warnings are always there. Someone always knows. Someone always speaks up. And someone always ignores them. The engineers at Morton Thiokol warned about the O-rings. They had data. They had evidence. They had years of testing. And NASA ignored them. The managers at Deepwater Horizon ignored the warnings about the blowout preventer. They had reports. They had inspections. They had evidence. And they ignored it. Listen to the warnings. Create a culture where people feel safe speaking up. Encourage dissent. Reward those who raise concerns. The person who speaks up might be the one who saves lives. Communication is the lifeblood of engineering. When it breaks down, disaster follows. The Hyatt Regency walkways collapsed because the engineers who changed the design didn't tell the engineers who did the calculations. The Boeing 737 MAX crashed because the engineers who designed the software didn't tell the pilots how it worked. Communicate clearly. Make sure everyone understands. Make sure there are no gaps. Make sure the information flows. Oversight is essential. It's the safety net. It's the last line of defense. The Seongsu Bridge collapsed because the inspectors didn't do their job. The Skyline Plaza collapsed because the building inspectors approved unsafe work. Maintain oversight. Create independent checks. Require verification. Don't rely on self-regulation. The people doing the work are not always the best judges of its safety. This is the principle that saves the most lives. Learn from the failures of others. Don't wait for your own tragedy to teach you the lesson. The aviation industry learned this lesson after Tenerife. They created a culture of crew resource management that has made flying one of the safest forms of transportation. The nuclear industry learned this lesson after 3 Mile Island. They created a culture of transparency that has made nuclear accidents increasingly rare. Learn from others. Study the disasters. Understand the causes. Apply the lessons. Don't wait for your own tragedy.
This is the principle that makes all the others possible. A culture of safety. A culture where safety comes first. A culture where warnings are taken seriously. A culture where people feel safe speaking up. A culture where cutting corners is not acceptable.
The Space Shuttle Challenger disaster happened because there was a culture of go fever.
The managers wanted to stay on schedule. They didn't want to hear bad news. They created a culture where warnings were ignored. The Boeing 737 MAX disaster happened because there was a culture of cost-cutting. The managers wanted to save money. They didn't want to hear bad news. They created a culture where safety was secondary. Build a culture of safety. Make it the foundation of your organization. Everything else depends on it. This is the hardest principle to accept. You're human. You make mistakes. You're not perfect. And no matter how good you are, you will fail sometimes. The engineers who designed the Hyatt Regency walkways were not incompetent. They were skilled professionals, and they made a mistake. The pilots who crashed the plane at Tenerife were not incompetent. They were experienced professionals, and they made a mistake. Accept your fallibility.
Acknowledge that you can be wrong. Build systems that compensate for your weaknesses. Create redundancies. Create backups. Create independent checks. This is the principle that never ends. Keep learning. Keep studying. Keep improving. The disasters will keep happening. The lessons will keep coming. And you need to keep learning. Henry Petrosky wrote that engineering is fundamentally about learning, about taking the lessons of the past and applying them to the future, about building on the successes and failures of those who came before. Keep learning. Read the accident reports. Study the investigations. Understand the causes. Apply the lessons. The moment you stop learning is the moment you start repeating the mistakes of the past. These are the principles for thinking about failure. They're not complicated. They're not difficult to understand, but they're hard to follow. They require discipline. They require humility. They require a willingness to question your assumptions.
They require a culture that values safety over speed. They require an organization that encourages dissent. They require individuals who are willing to admit when they're wrong, but they're worth it. Because they save lives. They prevent disasters. They make the world a better place. So as we end this journey, let's remember the stories we've shared. The bridges that fell. The buildings that crumbled. The ships that exploded. The systems that failed. Let's remember the people who died because we didn't learn fast enough. And let's commit to doing better. Let's build systems that are safe. Let's create cultures that value safety. Let's listen to the warnings. Let's communicate clearly. Let's maintain oversight. Let's learn from others. Let's build redundancy. Let's design for failure. Let's accept our fallibility. Let's keep learning. Because that's what engineering is really about. Not perfection, but progress. Not eliminating failure, but learning from it. Not building a world without disasters, but building a world where disasters are less frequent, less severe, and more survivable. That's the way forward. That's how we think about failure. We've spent 10 chapters exploring engineering disasters. We've looked at bridges that fell, buildings that crumbled, ships that exploded, and systems that failed. We've traced the cascades, analyzed the human factors, and learned the lessons. We've created a framework for thinking about failure that can guide us into the future. But there's one more thing we need to talk about. Something that connects all of this to your own life. The engineering mindset. You don't have to be an engineer to think like one. You don't have to design bridges or write code or build power plants. You just have to adopt a certain way of seeing the world. A way of thinking that questions assumptions, anticipates problems, and learns from mistakes. Let me show you what I mean. Think about the last time something went wrong in your life. Maybe your car broke down. Maybe your computer crashed. Maybe a project at work fell apart. What did you do? Did you panic? Did you blame someone else? Did you just accept it and move on? Or did you do something else? Did you ask why? Did you trace the chain of events? Did you look for the cascade? Did you try to understand what went wrong so you could prevent it from happening again? That's the engineering mindset. It's the ability to step back from a problem and analyze it systematically. It's the willingness to ask hard questions, to challenge assumptions, to accept blame when it's deserved, and to learn from mistakes. Now, let me give you a concrete example. Imagine you're driving to work and your car starts making a strange noise. Most people would ignore it. They'd turn up the radio. They'd hope it goes away. They'd assume everything is fine. An engineer wouldn't do that. An engineer would ask, what is that noise? Where is it coming from? What could be causing it? Is it serious? Should I stop and investigate? They'd be curious. They'd be cautious. They'd be willing to admit that they don't know what's happening and they need to find out. This is the engineering mindset in action. It's not about knowing everything. It's about being willing to find out. It's about being curious. It's about being humble enough to admit you don't know. Now think about how this applies to your life. How many times have you ignored a warning sign? How many times have you assumed everything was fine? How many times have you cut corners and hoped for the best? And how many times has that worked out for you? Probably most of the time. Most of the time things do work out. Most of the time our assumptions are correct. Most of the time the shortcuts don't cause any harm. But sometimes they do. Sometimes the cascade starts. Sometimes one small mistake leads to another, and suddenly everything falls apart. The engineering mindset is about recognizing those moments. It's about knowing when to stop and ask questions. It's about knowing when to be cautious. It's about knowing when to say, wait a minute, something doesn't feel right. Let me give you another example. Imagine you're planning a vacation. You book the flights, you book the hotel, you pack your bags. You assume everything will work out. You assume the flights will be on time. You assume the hotel will be as advertised. You assume the weather will be good. An engineer wouldn't do that. An engineer would plan for contingencies. They'd check the weather forecast and pack accordingly. They'd have a backup plan if the flights are delayed. They'd read the hotel reviews and look for red flags. They'd think about what could go wrong and prepare for it. This is the engineering mindset. It's not about being paranoid. It's about being prepared. It's about recognizing that things don't always go according to plan. It's about building resilience into your life. Now, let me talk about something more serious. The engineering mindset can save lives, not just in the abstract sense, but in a very real, immediate way. Think about the people who survived the collapse of the Hyatt Regency walkways. They didn't survive because they were lucky. They survived because they were paying attention. They heard the popping sounds. They recognized that something was wrong. They moved. They got out. They survived. The people who died were the ones who ignored the warnings. They assumed everything was fine. They didn't want to be the ones to panic. They stayed where they were. And they died. The engineering mindset is about paying attention. It's about recognizing the warning signs. It's about acting on them. It's about being willing to say, something is wrong and I need to do something about it. Now,
let me talk about how the engineering mindset can improve your decision-making.
We all make decisions every day. Some are small, some are large, some are trivial, some are life-changing. An engineer approaches decisions differently. They gather data. They analyze the options. They consider the trade-offs. They think about the consequences. They make decisions based on evidence, not emotion. They're willing to change their mind when new evidence emerges. They're willing to admit when they're wrong. Think about how this applies to your own decisions. How often do you make decisions based on emotion rather than evidence? How often do you stick with a decision even when it's clearly wrong? How often do you ignore data that contradicts your beliefs? The engineering mindset is about making better decisions. It's about being rational. It's about being objective. It's about being willing to change your mind. Now, let me talk about how the engineering mindset can help you learn from failure. We all fail. It's part of being human. But how we respond to failure matters.
Most people respond to failure with denial. They blame someone else. They make excuses. They refuse to accept responsibility. They learn nothing. They repeat the same mistakes. An engineer responds differently. They accept responsibility. They analyze what went wrong. They learn the lesson. They apply it to the future. They don't make the same mistake again. Think about the last time you failed at something. How did you respond? Did you blame someone else? Did you make excuses? Did you refuse to accept responsibility? Or did you learn the lesson? Did you figure out what went wrong? Did you change your approach? Did you do better next time? The engineering mindset is about learning from failure. It's about accepting responsibility. It's about being willing to be wrong. It's about using failure as a tool for growth. Now, let me bring this back to the big picture. The engineering mindset isn't just about individual decisions. It's about how we build systems,
how we create organizations, how we design the world around us. The disasters we've discussed in this story happened because someone didn't have the engineering mindset. Someone assumed. Someone cut corners. Someone ignored the warnings. Someone communicated poorly. Someone failed to learn. But the disasters also taught us something. They taught us what happens when we don't think like engineers. They taught us the consequences of ignoring the warning signs. They taught us the cost of cutting corners. They taught us the price of arrogance. And they also showed us the power of the engineering mindset, the ability to learn from failure, the willingness to question assumptions, the commitment to building better systems, the determination to make the world safer. So, what does this mean for you? It means you can adopt the engineering mindset. You can start thinking like an engineer. You can apply these principles to your own life. You can make better decisions.
You can learn from failure. You can build resilience. You can be prepared for the worst. It starts with a simple question. What if I'm wrong? What if my assumptions are incorrect? What if the thing I'm relying on fails? What if the system I'm part of breaks? What if the worst happens? Ask yourself that question. Let it guide your decisions. Let it shape your planning. Let it influence your behavior. And when things do go wrong, when the assumptions fail, when the system breaks, you'll be prepared. You'll have a plan. You'll be resilient. You'll survive. The engineering mindset isn't about being negative. It's about being realistic. It's about recognizing that the world is uncertain. It's about accepting that things can go wrong. It's about preparing for that possibility. Henry Petrosky wrote,
that engineering is fundamentally about anticipation, about thinking ahead, about imagining what could go wrong, about preparing for the worst. That's the engineering mindset.
And it's a mindset we can all adopt. So as we end this story, I want to leave you with one final thought. You don't have to be an engineer to think like one. You just have to be curious. You just have to be humble. You just have to be willing to question your assumptions. You just have to be ready to learn from failure. That's the engineering mindset. That's how we build a better world. That's how we prevent the next disaster. That's how we make the future safer for everyone. So here we are, the final chapter, 12 chapters, thousands of words, countless stories of disaster and recovery. We've traveled through time, from the twisting Tacoma Narrows Bridge in 1940 to the crumbling Hyatt Regency walkways in 1981, from the exploding Sansina in 1976 to the cascading software failures of 2023 and 24. We've seen how the world learns through failure, how each collapse, each explosion, each system crash becomes a lesson, how the lessons become new standards, new regulations, new ways of thinking, how the tragedies of the past make the future safer. But what does it all mean? What's the final lesson? What's the one thing we should take away from this entire journey? Let me tell you a story about the most important engineering disaster you've probably never heard of. In 1952, the de Havilland Comet was the most advanced passenger jet in the world. It was faster, higher, and more comfortable than anything else in the sky. It was the future of aviation. And then it started falling out of the sky. In 1953, a comet crashed near Calcutta, India. 23 people died. A few months later, another comet crashed near Rome, Italy. 35 people died. The cause was a mystery. The aircraft had been thoroughly tested. It had been certified as safe. And yet, it was killing people. The British government launched an investigation. They recovered the wreckage from the sea. They examined every piece. They tested every component. And finally, they discovered the cause. The comet had square windows. The corners of those windows were stress points. The pressure inside the cabin, combined with the forces of flight, created tiny cracks at the corners. The cracks grew with each flight. Eventually, they became large enough to cause a catastrophic failure. The plane broke apart in mid-air. The solution was simple. Round the corners of the windows, eliminate the stress points. The problem was solved. The comet was redesigned. The lessons were applied. And aviation became safer. But here's the thing. The lessons were learned through tragedy. People died because no one had thought about stress points in the corners of windows. No one had thought about how the pressure of the cabin would interact with the shape of the windows.
No one had thought about the cascade of failure that would eventually bring the plane down. This is the final lesson. The world is full of things we don't know, full of things we haven't anticipated, full of ways things can fail that we haven't imagined. And the only way to discover them is through experience, through trial and error, through failure. Now let me tell you why this matters. We live in a world of unprecedented complexity. Our systems are more interconnected than ever before. Our technologies are more powerful than ever before. Our challenges are more daunting than ever before. Climate change is changing the environment in ways we can't fully predict. Artificial intelligence is creating systems we can't fully understand. Cybersecurity is creating vulnerabilities we can't fully guard against. Global supply chains are creating interdependencies we can't fully manage. The disasters of the future will be different from the disasters of the past.
They won't just be bridges and buildings. There'll be power grids and financial systems. There'll be software updates and algorithmic biases. There'll be climate events and cyber attacks. There'll be cascading failures that span continents. But the lessons of the past still apply. The patterns are still the same. The cascade of failures, the breakdown of communication, the pressure to cut corners, the failure of oversight, the illusion of safety, the human factor. They're all still there. They just take new forms. So what do we do? How do we prepare for a future we can't predict? How do we build systems that are safe when we don't know what the threats will be? We do what engineers have always done. We learn from failure. We study the disasters. We analyze the causes. We apply the lessons. And we keep improving. We keep learning. We keep getting better. We build redundancy into our systems. We create independent checks. We maintain oversight. We encourage dissent. We listen to the warnings. We communicate clearly. We accept our fallibility. We keep learning. We adopt the engineering mindset. We question our assumptions. We anticipate failure. We design for the worst. We prepare for the unexpected. And we remember the final lesson. Failure is not the end. It's the beginning. It's the start of learning. It's the engine of progress. It's how we get better. Henry Petrosky wrote that engineering is fundamentally about learning. Learning from failure. Learning from mistakes. Learning from the past. And he's right. The history of engineering is the history of learning. The history of progress is the history of failure. Think about that for a moment. Every advancement in human civilization has been built on the failures of the past. The wheel was invented because someone tried to carry something and failed. The bridge was invented because someone tried to cross a river and failed. The airplane was invented because someone tried to fly and failed.
Failure is not something to be feared. It's something to be embraced. It's the engine of progress. It's the source of innovation. It's how we learn. Now, let me bring this back to you. You, the person listening to this story. You, the person who has traveled with us through 12 chapters of disaster and recovery. You, the person who has learned about the cascade of failure, the human factor, the illusion of safety, and the engineering mindset. What do you take away from this journey? What's the final lesson for you? Here it is. You can apply the engineering mindset to your own life. You can learn from failure. You can anticipate problems. You can build resilience. You can create systems that are safe. You can make better decisions. You can be prepared for the worst. You can question your assumptions. You can challenge the groupthink. You can speak up when something doesn't feel right. You can be the person who stops the cascade before it starts. You can accept your fallibility. You can admit when you're wrong. You can learn from your mistakes. You can do better next time. You can be curious. You can be willing to learn. You can be open to new ideas. You can be willing to change your mind. These are the lessons of engineering. They're not just for engineers. They're for everyone. They're for anyone who wants to build a better world. They're for anyone who wants to make the future safer. They're for anyone who wants to be ready for the unexpected. So as we end this journey, I want to leave you with one final thought. The world is uncertain. Things go wrong. Systems fail. Disasters happen.
But we don't have to be victims. We can be learners. We can be engineers. We can build a better world. It starts with a question. What if I'm wrong? What if my assumptions are incorrect? What if the system I'm part of breaks? What if the worst happens? Ask yourself that question. Let it guide your decisions. Let it shape your planning. Let it influence your behavior. And when things do go wrong, when the assumptions fail, when the system breaks, you'll be prepared. You'll have a plan. You'll be resilient. You'll survive. And you'll learn. You'll figure out what went wrong. You'll apply the lesson. You'll do better next time. You'll make the world a little safer. That's the final lesson. That's the legacy of every disaster we've discussed. That's the gift of every tragedy. They teach us. They make us better. They help us build a safer world. So thank you for joining me on this journey. Thank you for being curious. Thank you for being willing to learn. Thank you for being part of the solution. Now go out there and build something. Build a system. Build a relationship. Build a community. Build a better world. And when things go wrong, don't despair. Learn, adapt, improve, keep going. Because that's what engineers do. That's what humans do. We keep trying. We keep learning. We keep building. And we keep getting better. The end.